Okay, so my phone and my brain started overheating, so I had to take a little break, a much longer break. But I'm back. I think when my phone automatically stopped recording, I was searching for a polynomial inequality with a sign that's greater than or less than. Um, it does not have the equal to sign. So here's one example where the sign is a greater than. Over here, you see it on the number line that I put full dots because it's an equal to sign. But since it's just a greater than, I put just holes. And I do the same process. I put the factors in. If this is a negative factor, a negative coefficient, I put a negative coefficient over here, and I do the same process. And since it's just greater than, and these are all holes, I would put round brackets for my answers. And so that is solving polynomial inequalities. Union and intersection. Is quite confusing. Union is used when all values except between these two and 3, all values except 2 and 3, and intersection is used when it's all values between 0 and 5, as you can see here. I'm studying and learning, yes. Okay, so let's see. Now we come into simplifying rational equations. This slowly moves into graphing equations, and then we have logarithms. So just a quick overview. We're going to do rational equations, and then logarithmic equations, and then radians, and then trigonometry, trigonometric identities, and then solving trigonometric equations, and then it's over. And then I'll eat my lunch, which I've been waiting for a while. 30 minutes. I'm gonna try to do this in 30 minutes, hopefully. So, simplifying rational equations, it's very easy. Don't need to do this. And so we finally come into reciprocals, reciprocal, right? And so in many of these problems, you have a graph. You're gonna find the vertical asymptote, the horizontal asymptote. You're gonna find where the end behaviors are. You're gonna find the holes, right? This is not happen. Oh well, yeah, no, this can happen. You're gonna find the and so you're gonna find where the function intersects the horizontal asymptote, its turning points, and that's kind of how you're gonna graph the function. You're gonna find the main points, the important ones, and just slowly figure out. And so okay, reciprocal, reciprocal of a quadratic function, reciprocal of a cubic function, linear over linear function, and a parabolic asymptote. And so what you see that's common amongst all of these is that output circles around each the end behavior that I want to find, the y-intercept, the x-intercept. And so you need a whole bunch of separate calculations to find special key points on the graph. This one's very special. It has dividing the polynomial equations to find the, what is it? The parabolic asymptote, and you need to convert the standard form quotient into a vertex form in order to graph it. And so all of that is done in this small area. And behavior, it's, yep. Okay. So polynomial equation, it's reciprocal. The reciprocal of a linear equation is a reciprocal function. It's the same x-intercept. There's a lot to explain. I don't think I'm going to go through all of them. There are also lots of little small rules you need to remember. If the discriminant is negative, there is no intersection points. The function's translated up. If the function's translated to the left or right, the shape is going to be different. Maybe on your exam or tests, your teacher will just give you a function and say, without solving everything, you need to find the general shape of the function. That could be an exam question. If the quadratic looks like this, what areas, like the bottom of the graph, I don't know how to explain it. It's been a very long time. I guess I kind of see some similarities when the quadratic is in the negative quadrants. If it's pointing, if it's like a U shape pointing upward in the negative quadrants, it's upside down. And if it's pointing upwards in the positive quadrant, just that in behavior side, the x-intercept of the quadratic function, that's the vertical asymptote. Oh, right. The horizontal asymptote of all reciprocals of quadratic, linear, cubic, quintic, quartic, the horizontal asymptote will always be y equals 0. And there will always be 0 x-intercepts. So that's something you could remember to prevent, to save time on your exam. Okay, so on when two linear functions are divided by each other, it results in a reciprocal function that is translated along the xy plane. The horizontal asymptote is just the coefficients divided by each other. So here it's horizontal asymptote is y equals 2/3, and the vertical asymptote would just be the solution of the denominator. So x equals minus 2/3. And everything else would be the same. Now you have an x-intercept, and you have a horizontal asymptote. And now it gets a little more challenging. With a linear over quadratic function, you always have a horizontal asymptote, but also you might have the function passing through the horizontal asymptote. So that's slightly confusing. Let me see. How do you find the horizontal asymptote? Just right. Okay. So you just set as you put y equal to 0, and you solve for the x values. I don't need this. You solve for the x values. This is the x-intercept. The y-intercept is when x's are 0, when all the x values are 0. And you solve for the end behaviors and the behaviors as x approaches the horizontal asymptote and vertical asymptote. I guess it doesn't really explain the calculations over here, it just shows the answers, but my practice book, I think that covers it. So, right, to find the behavior as the function approaches negative infinity, positive infinity, or where the function approaches the vertical or horizontal asymptote, what you do is you just, if you're trying to find the behavior as x approaches negative infinity, you just put g of x, a really large negative number for g of x, and you solve your equation, and that would lead you to some number. Here in this case it's negative 0.0001, and that would be right below 0 over here. So you would know if you draw a graph, you would know the end behavior as at negative infinity is right there. You do the same thing for positive infinity, and it would also be negative 0.001, so it'd be really, really close to 0 on the right hand side. You know the, what is it? The vertical asymptotes, so you'll draw those. And then you do the same thing. So if you're gonna find the behavior of the function as x approaches negative 2 from both the left side and the right side. I'm going to find the behavior of the function as x approaches 2 from the left side and the right side. Let me see. So I've done that calculation here. So to find out at negative 2 and positive 2, right? You make negative 2 to find the behavior on the right side of negative 2. You put a value that's just negative 2.0.001. That's right on the right side of negative 2. And you solve for your function. You solve for the answer, and it shows some extremely large negative value. Let me see. Why does this say? Oh, okay. This is negative 2 on the left side because a larger negative number moves to the left, right? And so this value is right there. And since it's a large negative value, it points downwards. Negative 2 on the right hand side would be negative 1.99999, and it solves for a large positive number. So you know the end behaviors over there. You do the same thing for, let me draw this out larger. These are your key points. You would do the same for the asymptote on the right hand side. That would be right there, right there. And what else do you need now? The x-intercept, the y-intercept, and that's kind of all, I guess. You should know the general shape of the functions, a reciprocal function, so you don't unnecessarily have to solve for the local maximum. Okay, you solve for the y-intercept and be somewhere here. And just from looking at this function, you would find out the function looks like this. This connects here, and this connects here. Okay. For this function, same thing. You would find the vertical asymptote, you would find the horizontal asymptote, you would find the y-intercept, and you would find the x-intercept. You would find the end behaviors around the vertical asymptote, the end behaviors along the horizontal asymptote. And with that general knowledge, you can just connect the dots together. With a quadratic asymptote, same thing. You have a vertical asymptote. You have quadratic asymptote. You would find the end behaviors. And some other points, the x-intercepts and the y-intercept. So the way to find the behavior as x approaches the parabolic asymptote is quite confusing. It involves, it's also not something you would cover a lot in grade 12 math. The teacher, I remember my teachers wouldn't cover it. Like, we only had one practice problem on it, and we didn't go through it as much. This is oblique asymptote, and this is slant. And then suddenly an exam question would pop up, and I would be all scared. I won't be explaining it right now either. I'm short of time, but I guess just by looking at this, I'd hope you'd figure it out. I guess this is how university professors teach. Once you encounter something, like they won't teach it to you, they'll just show it to you. So I'm sorry if I'm doing this to you too. If you do need help, you can contact me if you're any of my friends. And I'll try my best to help you. For a quadratic over a quadratic function, a new thing gets added. And that is the whole. If any factors get cancelled out, the solution of x is a whole where nothing exists in that hole, in that area. Yep. And you take whatever you have here, and you solve for your x-intercept and y-intercept. You know that your vertical asymptote is 3 because it's a denominator. The horizontal asymptote is 1 because 1 divided by 1 is 1. This is where I explain oblique asymptotes a lot. So this will take a very long time to explain. But very simply, I'll try my best. Oh, wait, I guess this method is easier, but it's been wrong. Um, it didn't really help me. Like, I got a few questions wrong doing this method. Uh, okay, solving for n behaviors. Oh wait, this applies to all the problems. So yeah, this just explains how everything is done for all of the n behaviors. You see, just if you want to find the n behavior at vertical asymptote minus 5, you take what's to the left of it and what's to the right of it. And on the right hand side, if it's a large negative number, it just goes down. On the left hand side, if it's a large positive number, it just goes up. So, yep, for the parabolic asymptote, or slant oblique asymptote, it's quite difficult. So what you're trying to find is if the function is above, like if this is the asymptote, if this is the asymptote, you're trying to find if the function is over here or over here, right? And so what you do is you take a large value of x, it can be 20 or 200, and you plug it in to your parabolic equation, your parabolic asymptote equation, and your function equation, and you solve for the numbers. And it would give you some large number. So say that this is 345, and this is 344. At point 20,
Whoa, what's that? I just built a budgeting app in Base 44. Guys, Nina just built an app.
at point 20, which is over here, right? Cannot explain this really well. I hope that zooming in on this would help. especially zooming in on this part. I'm gonna move on. If you do need help on this, I guess you can contact me, and I'll try my best to figure it out. And now we jump into logarithms. It's the inside of a logarithm is called the argument. All logs contains a log base 10, and a log equation is always solving for an exponent, and so log base 10x equals a. You're taking a base 10 to the power of the exponent equals x. This is the equation, and you're trying to solve for the exponent. If you want to find out what like 4 is, it would probably take an extremely long time to find out like what decimal number is 4 exactly. So you take log the base 10, you bring 4 to the other side, and you put a in the denominator. Log 4 is 0.602. And so if you take this back to the original, 10 to the power of 0.602 is a number that's really close to 4. So solving logarithmic equations. Huh. Oh, okay. So you start with this first. I guess you could ignore this for now. What I've said before is the same as what's here. As you've seen before, if you want to find the inverse, you just switch the x and y values. Yeah, you just switch the x and y values, and you get x equals to a y. And to solve for y, you get log base a exponent y. Oh wait, log base a. You bring x to the other side. You put that here, and the exponent equals to y. So oh yeah, and these restrictions are really important. You'll know why when you graph them. X can only be greater than 0. Yep. Here are some common logarithmic rules. Log x is the same as log base 10x. And if you have a base that's not 10, you do log x divided by log y. When you divide them, the base automatically turns into 10. And so you'll still be able to find your answer with a different base. There is a different kind of, when you replace 10 with y, or Euler's constant, which is in irrational numbers, it's called Euler's number, you get ln x. So log base ex is the same as ln x. Yep. Other properties of logarithms: log base 6 1 is 0, log base x times x is 1, where these two numbers are the same. These two variables are the same. Log base 5 to the power of x is x. 6 to the power of log base 6 x equals y. Huh. Okay. When two logarithms are added together, you can put them all into one area, one log, and multiply them together. When they're subtracted, they can be divided. When there is a power, such as right here, when there's a power inside the log, you can bring the power and multiply it by the log x. I've explained it a bit, but it really uses these two properties and the change of base formula I explained before. So here, it can be brought in and multiplied, and base 10 to the power of 1, bring this to the other side, and then you can solve for the x's. And then these two must use the inequalities table like we used before, like this, and all the negative values if this solves for a negative value, it's rejected, and if it solves for positive, it's accepted. I'm not sure why. Let's see. Applications of logarithms are used very extensively. In case you cannot read them, this is the formula to find pH. This is the formula to find the intensity of sound in decibels. This is the formula for the intensity of an earthquake. This is half-life, can be used in radioactive materials doubling time, and this is percent growth or decay, or compound interest. Okay. Alright, so radians. It has been about 3 hours since I've started this review. So I really, really, really want to wrap this up. I guess my next video is going to be a time lapse of me filling up my calculus notes. I guess I've explained this quite a bit in my previous video. 1 radian is 180 degrees. If you want to convert from radians to degrees, you multiply it by 180 over pi. And degrees to radians, you multiply it by pi over 180. Radians in degrees is equals to the arc length divided by the radius of a circle. Even though this is quite important, I think I'm going to skip over these. These equations, some of them you need to memorize, some derives each other. I talked about this last time. Okay, that is the end of my notebook. I am quite tired, so I'm gonna go eat my lunch now. My apologies for not being able to complete Radiance properly, but I am quite hungry, so I must stop the video now. Thanks for watching.